just joining.
This call is now being recorded.
Okay, good evening. I'm going to start. Am I audible?
Yes, sir.
Okay, good. So I'm just going to give you a quick overview of what is there in the first week and the next couple of weeks. And because the problem sheet is due only tomorrow, we will discuss them next week. But for now, I'm just going to give you an overview of what we have done. So we've set some terminologies. So for us, the data structure problem consists of some data plus operations. Okay, so this is a template. This is the formulation clarity I want you to have when you talk about data structures, right? So every problem comes with some set of data, and these are the operations. Because this, bulk of what you're going to learn in this is this kind of formulations much more than the algorithms or techniques, because that's something you already know, you've done it. But how do you structure it? How motivate it? That's the whole point. Okay, so we saw, you know, last in, first in, first out kind of operations where I have a bunch of data coming in. I want to extract the one that came the earliest or the one that came the latest, and then I want to insert. And this was implemented using a simple array or a linked list, and you had constant time for operations. Okay, so again, the problem, the implementation, and various implementations. You analyze them, understand the cost, and what is the cost. That's constant time. That's what we did. Then we talked about search, where we want to organize a set of numbers and be able to answer a query about given an element, is it there? And we said sorted array is a nice solution. You can use binary search, and we did an analysis of it and said it takes order log n time. Okay, and the example, the problem sheet contains various variations of binary search. So it's not just about searching in a sorted array. There are, binary search is so fundamental. A, you need to understand the running time, and B, understand some interesting applications or interesting variations, and that's what the problem sheet does it. And at this point, I left open the question, what about search plus I also want to support insert. Okay. And there we said I could just do sorted array, but it has its own problems. Search may take log n time, which we have seen, but insert takes order n time. Okay. Well, then we said, why not use sorted list, a linked list? Can anybody tell me what is the problem with that, or what is the running times for sorted linked list? Yeah. What are the running times for search or insert in a sorted linked list? Okay, this is all there in the first video. So I hope you can hear me. I want somebody to answer. Yeah? Yeah, you can unmute and answer. You may not be looking at the chat all the time. Yes, what takes order n time, Ashupal? The search or insert or both? If you're saying something, I'm not able to hear. If nobody
Sir,
is yeah.
search takes order n time and insert takes constant time.
After we have search where to insert, you can it takes constant time. But to search where to insert, why does it take constant time? Order n time for search, even if it is sorted.
Because we cannot access the ith element.
Very nice. Yes, exactly. Okay. So this is important to get across very early on if you're teaching it, that and our goal in this whole course, you can think of it roughly as a holy grail, is to support all these operations in order log n time. And I have given motivation for why log n is important and so on. So this is where things are. Okay. So we need a solution where you can support in log n time. This is where we left in the first set of videos. And then the other operation we looked at was you want to support insert, and so you can think of it as a problem, it's a game, puzzle. This is the way you want to motivate, find max. Here also, after trying various operations, we said, oh, just keep track of max. It's a very simple solution. You can do both operations in constant time. But if I also want to do insert and delete max, you have a problem. Okay, so this is how the first week ends. Okay, in fact, I want you to just sort of motivate your the entire course through these examples gently, over 2-3 lectures maybe, and just leave it at that as a trailer curiosity about what is the best way to do it. Now, to be able to make them understand it, you have to talk about complexity and talk about binary search running time, and say that if you want to use the same structures, you're going to be stuck with some linear time. And this is where the first week ends. Now in the second week, essentially we give complete solution for both these problems in logarithmic time, and in fact that's bulk of the data structures course. So in the next 2-3 weeks sessions, videos, about 6-7 lectures, the entire solution is given. The data structures course is more or less over. Okay, so I'll again tell you what the solutions are, but before that, any questions or comments? Ratikanta has a question or what? Anybody has any comment on this about first week lectures? Problem sheets we'll discuss next week, but any questions on the videos?
Hello, sir. Hello.
Go ahead, yes.
In binary search, we are actually dividing the problem into three parts.
Okay, depending on what you...
First is mid element,
Mhm.
and then less than that, and
Yeah.
greater than that. So three part. So my question is that is it belongs to divide and conquer or only divide? Because we are not solving all the sub problem. We are just solving the two sub problem, not all. Mid and either less or either greater than.
It is divide and conquer. It doesn't matter. I mean, divide and conquer is a technique where you divide the input in multiple parts and somehow solve each one of them, or one of them. Take advantage of the input and do something. Yeah. So it is one of the divide and conquer techniques.
Thank you.
Okay. Any other question? Okay. So again, these are the names, heuristics. Get on to the problems, the complexity, the math. Okay. Those are more important than whether you call it divide and conquer or divide or conquer. It doesn't matter. Okay. Okay. So I hope you appreciate that setting of this stage of this, the way to motivate problems, and stop there and ask questions about how do you do it, and arouse the curiosity of the students about, oh, something big is going to come subsequently where these problems are going to be solved. And then, okay, so then once you realize that sorted array or sorted linked list is not enough to support search and insert, what do I mean by not enough? Can somebody give me a quick answer? Sorted array and sorted linked list are not good enough to support search and insert operations. What do I mean by good enough?
Not of order log n time.
Exactly. Very nice. Yes, that's the goal. So again, if you don't do complexity, you won't be able to say it and make them appreciate it, right? Yes. So they're not good enough, meaning that one of the operations or maybe both operations take linear time. So you need some other structure. And this is where we get into the notion of trees. We have seen arrays and linked list are basic axiomatic structures for data structures. Now we move on to trees. So the reason we want to get into trees needs to be motivated this way. Okay. So then the way we motivate trees is by saying, okay, so suppose I have if this is the list where, sorted array where I'm trying to do search and insert, we create this tree modeling the binary search we will do. Now we have a tree, a two-dimensional tree, and notice that if I want to search for some key, let's say 16, I will compare it with the 21. 16 is less, so I go left. 16 is bigger than 15, so I go right. 16 is less than 17, so I come here, and I know that if at all 16 has to be here, it has to be in this box. Since it's not there, I can just insert it. So in some sense, it's the best of array and a linked list. That yes, linked list, you cannot index it, but here, the tree structure gives you to index certain portions, navigate in certain way, and you can also insert a new element without pushing elements as you would do it in an array. So it looks like we have solved the problem because the height of the tree is log n, that you can search and insert in log n by this tree, what is called binary search tree. But then again, even this is not enough. Why is it not enough?
Because we have to start from the root and go one by one level down, and it will
Right, but
be a
that's just
linear.
log n. That's not bad because the height of the tree is log n. So you start from the root, go left or right. So you just pick one node at every level, and you can search. You can also insert.
Still, it can be sometime n if it is going one way only.
What do you mean by n? I don't understand.
So if all the elements are in one order, like increasing or decreasing, then we have
It
to
is in
go.
increasing order. What do you mean? All the elements are in increasing order only. If you look at this array, all elements are in increasing order, which I have modeled it like a tree.
Yes, so but we have taken like 21 as the root node. Suppose we
Right?
start from 40 and then go gradually. So every element
But
will
you
come there.
don't you don't start from 40, start in 21.
Okay.
You create the tree, right? So you create it in a way that the middle element is at the root, the left is the middle of the left side, and the right is the middle of the right set,
There
and
may be
so on.
skewing problems.
Yeah, what is
Skewing.
the skewing problem? Can you explain what that means?
If I get some ordered values, then I go
So,
to the
yes, you should keep in mind our data structure problem is not for one insert or one search,
yes, sir.
right? You are given some data, let's say 10,000 numbers, you organize it, and after that, continuous stream of search and insert are coming. Okay, so for this one insert, yes, you can do it in log n time, set it up in a nice way that its height is log n. But subsequently, if I have a lot of elements are coming like this and inserting, then no longer your 21 is the middle element. And so you no longer you have this great benefit of the height of the tree being log n. It can become a skewed tree, and the height can become order n, and
N.
so
Yes,
you lose the benefit of search and insert. Okay, so don't do binary search bang right away. Binary search tree, I'm saying. Start from sorted array, sorted linked list. You figure out that you are not able to do in logarithmic time, create this tree, but then the tree gives an idea like we have solved the problem, but you have solved it for one insert, one search. But if I am continuously inserting elements, then the tree is no longer nicely balanced. It can become skewed. So we need what?
balanced search tree.
Balanced binary search tree.
Yes, search tree.
So
ABL. Yes.
yes. So you need to again motivate by the need for balanced binary search tree. So this is binary search tree where you have a root, anything to the left is smaller, anything to the right is bigger everywhere, and you create this. This helps you to search in time proportional to the height of the tree, because you check one node at every level. But the height can become very large very soon when you insert elements. So you need to maintain more structure. So to maintain balance. What is that extra structure? Well, notice that, all of them, AVL or B trees, red black tree,
Red black tree. Yes, sir.
all of them are balanced binary search tree. All of them maintain this balance by some extra condition which tells you something about the structure of the tree. Okay, so first thing you need to do is that with that extra condition, the height will become log n all the time, as long as, so once you have defined them, all the details are there in the videos, but I'm just going to say step 1, prove order log n height with the extra structure condition. Okay, I would have done it for AVL tree in the videos. In the next week, it's coming. So this is the first step. Once you do this, good. Now, search is log n, because search you are not modifying the elements, but it creates some complication for insert and delete. Why? Because insert is no longer like so easy that the way we did it here, we compared and then did and found a gap and then we inserted. It's not as simple as that. Why? Yes, anybody? If you remember, insert in an AVL tree, why is it not as simple as I search, start from the root, I follow through the path and I found a gap and I go and insert my new element? Why is it not enough?
The tree may not be balanced.
What do I mean by
check.
that? What does it mean?
Left should
Balance
be
is a very
lesser.
loose word. Now you should talk about
Yes,
little more mathematically. So we have two conditions on my tree. One is that anything to the left is smaller, anything to the right is bigger is one condition. The second condition is the AVL tree structure condition, which tells you that left and right the difference is at most 1. Or B tree will have some other condition. Red black tree will have some other condition. Okay. So the problem now is after you have done this insertion, anything to the left is smaller, anything to the right bigger condition is satisfied. You don't have to worry about that. But the additional structure you have imposed may not be satisfied. So the insertion routine becomes more complicated. You have a huge number of case analysis to ensure that the new thing is fixed. The structure is maintained. Why is the structure maintenance important? Because that's what makes the height order log n. That's because that's what we prove, step 1. So step 2, need to do more work to maintain the structure. After insertion and deletion. If you set this big stage here, then people will appreciate all your complicated insertion algorithm and deletion algorithm, right? AVL tree or B tree, in every structure, the insertion is involved. You are going through, if this happens, do these rotations. If that happens, do these rotations. You're doing all that simply because we want to maintain this additional condition beyond left tree smaller, right tree bigger. And why do we need this additional condition? Because that's what makes the height order log n. Why is the height order log n if the additional condition is maintained? That's what is proved in step 1. So the whole data structure is all about carrying these constraints, carrying all this invariance. So once you say structure, these conditions must be satisfied. But when you do the operations, they may be violated. So you need extra work to fix them to make sure these conditions are violated. Why are these conditions needed? Because that's what helps you to support these operations in log n time. So this picture is what I want to convey. Once, the detailed implementations inside the AVL tree or red black tree are important. You do it once, but why they are important is something you need to convey in this way. Okay, so this is one, I think, couple of 2-3 lectures we do, and then I talk about supporting insert and delete max. These are the priority queue operations. Again, AVL tree can do in order log n time. So if we care about only log n time, AVL trees are good enough, but heaps are much simpler, uses only an array to support these two operations. You don't need pointers, no tree, no pointers. So that's the next set of slides which talk about the heaps. Again, how do you insert into a heap? How do you build a heap? How do you delete the maximum? And all are implementations, very simple. You need to do them. And I think I would have done a little bit on that. But the whole point is why, so heaps give a very simple structure to support these operations. And at the cost of what? What is the problem with heap? Can anybody tell me why? If I just want to support these two operations, people who already know these stuff, why can't I just settle down with AVL tree, and why do I need heap? Or alternatively, what is it something we cannot do in a heap easily? Okay, I'll answer these questions. You can go and look at the slides and understand them. Okay. Well, you can insert. Now, you can insert into a heap in log n time, because how do I deal with it? A structure which I cannot even insert something, I have a problem. Of course, I can insert it because these are the two operations I want to support. So I should be able to do insert and delete max. But compared to an AVL tree, there is something you cannot do in heap easily. I leave it to you. Think about it. We can get back to it next time. But especially if you are people who are already teaching these courses, you should know answer to these questions, and hopefully, the purpose of these lectures to shed light on these questions. Okay, so essentially, bulk of data structures course is about these two big data structures. There are more variations beyond AVL trees and heaps, and then we will look at them all. So by the end of this next 4 or 5 hours of videos, the whole data structures course will be over. Okay, so I'm going to give you next 2-3 weeks to do the next problem sheet, and I will ask Kirtana to release the next set of videos. But I want to make sure that you have most of you have a break time now. So take advantage of them and look at these things. And the data structures will be over in another couple of weeks of lectures, and then we'll move on to algorithms. Okay, and this is it. The whole course is about supporting these two operations. So you build towards them, and then get onto the details of implementation of these structures. That's what bulk of data structures course is about. Okay, now I will stop. This is sort of a trailer for what's coming in the next few lectures. Yes, so this one is for next week. I just gave you a trailer of what is coming in the next set of videos. Yeah. Yeah, I know. Week 1 is over. Problem sheet is due tomorrow. Solutions. I will discuss the problems next week. But you will get the next couple of weeks of lectures very soon, and that will cover the bulk of the core of data structures. Okay, so any questions or comments?
Sir, you said about advanced problem statements.
Yes.
Sir, how we can get it, sir?
Just send me an email.
Email to
Me.
yes, sir. Yes,
I
sir.
think the emails are all there in the first video or second videos.
Yes, sir. I will look into it. Thank you, sir.
Yeah. So here is the email address anyway, if in case it's vraman1311@gmail.com or vraman@imsc.res.in. Yeah, if you look at the first or second week slides, you will see all these email addresses. My email address, Keetana, who's in charge for NPTEL organization, and then Devi Amini, who is the TA for this course. But yeah, for getting advanced problem, just send me an email. Because I may want to have a discussion with you to understand your level and then send you questions. Yeah.
Thank you, sir.
Okay. Any other questions? Again, I want you to just take advantage of these weekly sessions by asking clarifying questions on the videos and get deeper into them. It's a math problem solving course. Yeah, that's the way the course should be taught. So yeah. Okay, so if there are no questions or comments, I'll see you next week.
Thank you, sir.
Okay.
Thank you, sir.
So Ratikanta, you want to ask the question? You can unmute and ask. Okay, fine. Okay, thank you. See you next week then. Bye.